All right, we are on section 10.2. Thanks for being here. Hypothesis tests for a population proportion. So here's where we get to see how this works, but not the nuts and bolts quite yet. We've got some theory to go through. Section 1, boy, wasn't that a killer. But hopefully we start getting some things cemented in place and we work through the process. There are actually two ways we go through. There is a logical a classical method and a probability method. We're going to go through both. This is not the practical how-to, but the why it works part of the lecture. In fact, most of this is the why it works, but I just would implore you to stay with me as we go through this. We're going to start with this idea of this research about banning cell phone use while driving. Consider this for quite a while. A researcher obtains a random sample of 1,000 people and finds that 534 of them are in favor of banning cell phone use while driving, which means that proportion is 53.4%. So now consider the following two people. The first person says, you know what? That seems to show that we're split 50-50. 50% of the population thinks we should ban and 50% think we shouldn't. While the second person says, you know, even though 53.4 is close to 50 and very well could be the same as 50, I think there's enough statistically significant evidence here to say that more than 50% think we should ban cell phones while driving, right? So these are the two people. Person one that thinks the population split 50-50. Person two, who we're going to call the researcher, thinks the data supports that the majority of the population is in favor of banning cell phones while driving. So what we have to do then is ask, well, what does the data say? Does this data suggest that it's split 50-50, or does the data suggest that more than 50% think we should ban? And to answer this question, we have to decide if 53.4% is a normal amount of variability from a population that is 50%. Maybe you can start thinking through some of these ideas of the null hypothesis. The null hypothesis is going to be the population proportion equals 0.5. And we're going to see how likely it is that a random sample would show a 0.534. In other words, would it be unusual to obtain a sample proportion of 53.4 from a population whose proportion is 50? Is there any statistically significant mathematical evidence? So when observed results are unlikely under the assumption that the null hypothesis is true, we say that those observed results are statistically significant. They make us change what we assume to be true. That's what makes it significant, all right? And when that happens, that's when we reject the null hypothesis. So to determine if this sample of 534 is significant, we build a probability model, a normal curve, based on that. And what we do, see if there's anything repetitive in this. Okay, so and when we assume that 0.5 is true, we'll see if it's unusual, and if it is unusual, we'll reject the null in favor of the alternative. 0.5 is true. That's our null hypothesis. 0.5 is the true proportion. We're going to find out that that's either true or false because the 0.534 is going to be on the high side, and maybe it even approaches that red zone of unusual, right? So we have to figure that out. And to build a probability model, it's a normal curve. We've got to figure out what the mean and standard deviation are of our situation. Well, that's based on our the stated population proportion is our mu. This goes back to one of the previous chapters, right? That's 0.5. And then the standard deviation is going to be 0.5 times 1 minus 0.5 divided by 1,000 square rooted. We find out that that's 0.016. So now look, we've got our mean and standard deviation. We can build a normal curve. Okay, so if we build a normal curve with a 0.5 and a standard deviation of 0.016, we can start to see where some boundaries might start showing up. You know, remember the 68, 95, 99.7 idea. Those are the classical boundaries, but what we're looking for is how many standard deviations is actually too many. Clearly, one standard deviation higher and lower, that's not statistically significant. That's pretty usual there, right? Is 2, is 2.5, is 1.5, all these different things. And those standard deviations depends on our value of A. Or sorry, depends on our value of alpha. Whatever our value of alpha is, that determines where we are. And if we went back to the previous slide, we could see. Well, I'll show you the chart next and see if we can get dizzy by it. This table is in your text. It's on that PDF charts that I uploaded. It's right here for you. But what this is saying, if we have a different value of alpha as given, maybe 10%, 5%, or 1%, and we have our left, right, or two-tailed test, let me pick one of these situations. I'm going to pick this one right here. I'm going to pick a 5% alpha and a right tail. And if I draw this out, what this is saying is, if this is an area of 0.05 and this is an area of 0.95 for a total area of 100%, then this right here is our mean. This value right here is a z-score of 1.645. If you are 1.645 standard deviations above the mean, then you have cut off an area equal to 5%, 0.05. So if we're looking for a z-score that's going to be unusual, we just have to compare that z-score to this critical value, a boundary, a critical value of 1.645. So we're going to find the z-score of 534 out of 1,000. Whatever that z-score is, we're going to compare it to this boundary of 1.645 if we have an alpha of 0.5. Now, if we have an alpha of 10%, well, that's going to be an area that's more, which means the z-score is actually going to be less. It's less far away. If we have a 1% alpha, that's a very small area. We've got to go quite a ways out there, all the way to 2.33. You notice these two values are the same, just one's positive, one's negative. Why is there a two-tailed test that these numbers are different? Well, if the alpha is 10% and we have two tails, we take that 10% and cut it in half, 5% here and 5% here, which is why the two-tailed number for 10% is the same as the single tail numbers for 5%, because this 10% is cutting off two chunks of 5% each. The 10% value is cutting off two chunks of 5% each. So we have a plus or minus tail there to show that it's either statistically significant on the low side or on the high side. Okay, so hopefully that's enough to see what's going on with those critical values. Again, nothing practical yet, just hang out with the theory. For our situation, let's say the researchers decide on a 5%, right? Which is why we found our critical value to be 1.645. Okay, and I know that it's a right tail because the researcher thinks the proportion is greater than the null of 0.5. So all we've got to do then is we figure out the z-score of 53.4%. And how do you find the z-score? Well, it goes way back, right? You just take the value that we have minus the mean divided by the standard deviation. We find out that 534 is actually 2.125 standard deviations above the mean. That is way in the red zone, right? Our boundary is 1.645. We have a z-score of 2.125. This is highly unusual. It is very unusual. And what does that mean? Let me show you a picture of what's going on. That means that we're going to reject the null hypothesis. Why would we reject the null hypothesis? And again, here is our boundary for the red zone at 1.645. And we found a z-score that is at 2.125. There is no way that a random sample of people is going to give a proportion of 53.4% if the true proportion of the United States is 0.5. It's just, you're not going to get that. You're only going to get that a very small portion of the time. Maybe you'll get it, right? It could happen. How likely is it to happen? Not very likely at all. And because it's not likely to happen, we can say that, well, either your statistics were done poorly or there's something wrong with your basic assumption. And if your basic assumption was 0.5, throw it out, because that 0.5 assumption doesn't play out with what the data shows. Okay? This is a conclusion. That this kind of summarizes the classical method, method number one. If the sample proportion is too many standard deviations away from the proportion stated in the null, then we reject the null. What is too many standard deviations? That's all based on the alpha value and the table previously shown. Okay? All right. So now, we're going to go through the exact same problem again using a probability method as opposed to the classical method. Okay? So that's the probability method. Here it goes. A second criteria we may use for testing is to determine, not based on standard deviations, but what is the probability of actually getting 534 out of 1,000? And if the probability is less than our alpha, then we know that we should reject the null. If it's only a 1 or a 2% chance that we get a 534 out of 1,000, and we've set our alpha at 5%, then we can say the chance of getting this is in the red zone again, which means we can throw out the null. Okay? How do we compute the probability, which is also called the p-value, and pretty much for the rest of the slides we'll see it as the p-value. We can compute that using the normal model, which we did with StatCrunch, right? What we're looking for is the region of the graph representing the probability of 0.534 or greater. And we can use StatCrunch with that value. I put it up here as a screen. We've seen this kind of screen before, right? The normal calculator, I just put in a mean of 0.5, a standard deviation of 0.16, and I want to know what's the area of this curve greater than 0.534. And it turns out that the area is 0.017. That's the probability. The probability of getting 0.534 or higher is a 1.7% chance. What's our alpha again? 5%? So the probability of getting this is quite a bit less than 5%. It's only 1.7% chance. If it's that low, guess what we should probably do with the null hypothesis? Reject it, just like we did before when the standard deviation was 2.125 standard deviations higher. We only need to get to 1.6. We only need to get to a probability of 5%. We had a probability of 1.7%. That's not nearly likely enough for us to keep the hypothesis. So it's pretty small. It is less than the value of alpha. So we should reject the idea of a population proportion of 50%. Because if it were true, the probability of seeing a 53.4 wouldn't be as low as 1.7. right? I think that's kind of a typo in that. I'll have to fix that. If it were true, our probability of seeing, it's not a typo. If it were true, our probability of seeing 53.4 is only 1.7%. That doesn't happen. That's why we reject it as being false. Okay? Whew. All right. So that is that's the theory. And now we get on to the stats. And I think I'm going to stop the video here. Because you probably won't watch this video again, but you might watch the practical stuff a couple times, which means the next video is going to be the rest of section 2 along with all of section 3. It's a Z test and a T test. Thanks for watching this one, and hang on, click play on the next video and you'll see the practical stuff actually worked out.